Bismillahirrahmanirrahim. Dear students, today I am going to discuss with you Wittig reaction, which is used for the synthesis of alkenes also. Mainly we will discuss in this lecture the introduction to Wittig reaction, the discussion of the reacting species, basis, the overall mechanism of the reaction, and then step-by-step mechanism of the reaction. And in the end, shall discuss the synthetic applications of this reaction. In 1954, G. Wittig introduced this reaction, and there have been many modifications made in this reaction by the other scientists. But here we are to discuss mainly about this reaction. The first reacting species for this reaction is triphenylphosphine. Triphenylphosphine, which is reacted with alkyl halides to produce phosphonium salts. These phosphonium salts are converted into phosphorane by the use of a base. The phosphorane, also known as phosphorus halides, are the first main reactant which reacts with the aldehydes or ketones to produce alkenes. This reaction is mainly for the production of alkenes from aldehydes or ketones, like some other reactions as we have discussed, HWE reaction, etc. Overall reaction is given here. Triphenylphosphine reacts with alkyl halide to produce phosphonium salts, which in the presence of base is converted into phosphorus halide. This phosphorus halide reacts with ketone to produce triphenylphosphine oxide and corresponding alkene. Here is the first reactant involved in these reactions is phosphorane. We will discuss about first phosphine, then phosphonium salt, and then phosphorane. All of these are organophosphorus compounds. Phosphine or phosphine is normally produced by the reaction of phosphorus trihalide, trichloride, tribromide with Gigner agent like phenyl magnesium chloride, or alkyl lithium like phenyl lithium, or phenyl chloride in the presence of sodium, and we get phosphine or triphenyl phosphine along with other products. Phosphine or phosphine are the compounds in which phosphorus is normally bonded to three different species. That is, phosphorus is showing three bonds. When this phosphorus showing three bond makes another bond, that is phosphorus with four bond, then we name it phosphonium salt. Here are three different types of phosphonium salts. First is simply phosphonium cation, and second is the protonated organophosphine cation, which has three alkyl groups and one hydrogen, and this is tetraorganophosphonium cation, which bears four alkyl groups with phosphorus cation. And in the end, phosphorane is the compounds in which phosphorus shows five bonds. That is, phosphorus is pentavalent. Phosphorus will attach to five alkyl groups, or phosphorus attached to four species, four alkyl, three with single bond and one with double bond, but four groups are carbon, then it is known as phosphorane. The valency, the trivalent phosphorus, you can justify through the three unpaired electron in the valence shell of phosphorus, and fourth bond is can be justified through coordinate covalent bond found by the lone pair of phosphorus with the fourth atom, and the pentavalency of phosphorus can be justified through five unpaired electron which are achieved when you excite electron from 3s orbital of the phosphorus into 3d, and we get 5 unpaired electron which show 5 bonds. Here we discuss the first reactant of this reaction, phosphorane or phosphorus gylide. Phosphoranes are also called phosphorus gylide or phosphonium gylide. Gylide is basically compound having an uncharged molecule containing a negatively charged carbon atom directly bonded to a positively charged atom of sulfur, phosphorus, nitrogen, or another element like oxygen. Gylide is a species, in simple words, gylide is a species with opposite formal charges on adjacent atoms. Here you can see the two forms of phosphorane. First form is called phosphorine form or Yelene form, in which double bond is present, and the second form is called Yelide form, in which two formal charges have been shown, negative on carbon and positive on phosphorus. This thing is simply like you show dative bond or coordinate covalent bond, and the negative charge on oxygen and carbon and positive charge on phosphorus can also be justified through the electronegativity, that carbon has more electronegativity, that is 2.5, and phosphorus has less electronegativity, that is 2.2, and therefore it bears positive and that bears carbon bears negative charge. Carbon bears a nucleophilic character due to this negative charge and attacks on the carbonyl of the aldehydes or ketones. In addition to phosphorus gylides, there are other examples of atoms like sulfur gylides, nitrogen gylides, and oxygen gylides also. There are two types of phosphorus gylides. One is unstabilized phosphorus gylide and the other is stabilized phosphorus gylide. In unstabilized phosphorus gylide, these have either hydrogen or alkyl group connected to the carbon atom present at alpha position, that is directly attached to the phosphorus of triphenylphosphine. And the alkyl groups are electron donating group, as we know, and so they destabilize the charge separation in the gylide form. Here are two forms are shown, Yelene form and the gylide form. In gylide form there is charge separation, positive on phosphorus, negative on carbon, but due to electron donating group this charge separation is destabilized, and therefore this molecule remains most of the time into its Gylene form, which becomes more stable, and so it predominates in the reactions, and all the reactions of unstabilized phosphorus gylide occur through this form. In case of stabilized phosphorus gylide, the substituents on the carbon atom must be ones that can stabilize the negative charge by delocalization. That is, they have carbonyl group etc., which can stabilize the charge through resonance or conjugation. Since charge stabilization is achieved through resonance or delocalization, the gylide form predominates. So in this case, that is stabilized phosphorus gylide form predominates and the reaction occur through this form. You can see here this is Yelene form and this is the gylide form, which is stabilized through resonance by this carbonyl group of ester attached to the alpha carbon. Here is the alkylating agent which is used in the preparation of phosphoranes. These alkylated agents can be alkyl, simply alkyl halides, or alkyl sulfonates. The nature of the alkyl group used defines the nature of the phosphorus gylide, that is, it will be stabilized phosphorus gylide or unstabilized phosphorus gylide, because if it contains electron donating species only, then it will form stabilized unstabilized phosphorus halide. And if this alkyl halide contains electron withdrawing species or conjugating species, then this will form stabilized phosphorus halide. In case of unstabilized phosphorus halides, the reaction occurs through Gilene form, as we have discussed earlier, and this will produce Z alkene predominantly. And in case of stabilized phosphorus halides, the reaction occurs through Gilide form, and the reaction predominantly form E alkene. The different bases used to produce phosphorus halide from phosphonium salt are alkyl lithium most of the time, and in addition to it, there are some other examples like sodium hydride, lithium hydride, sodium amide, etc., which can also be used as a base to deprotonate the phosphonium salt to convert it into Gilene form, or to convert it into phosphorus halide. Here is the complete mechanism of the reaction, where triphenylphosphine first reacts with alkyl halide through SN2 reaction mechanism and forms the phosphonium salt. This phosphonium salt further reacts with the base to produce phosphorus halide. Phosphorus halide then reacts with the aldehyde or ketone in a 2+2 cycloaddition manner and produce a cyclic compound having 4-membered ring that is also called oxaphosphetane intermediate. This oxaphosphetane intermediate is further converted into triphenylphosphonium oxide and corresponding alkene. Here is the first step of the reaction, that is formation of phosphonium salt from triphenylphosphine. Triphenylphosphine is made to react with alkyl halide through SN2 reaction mechanism. And triphenyl acts as a nucleophile due to presence of lone pair on phosphorus, which directly attacks on the alpha carbon of alkyl halide to remove the halo group in an SN2 reaction mechanism. SN2 reaction mechanism means that we can control this reaction through the conditions which are related to SN2 reaction mechanism. That is, it is a second order reaction. It depends upon the concentration of both of the reactants and so on. The nucleophilicity of phosphorus is greater than that of nitrogen due to large size. Here, if we compare the nucleophilic character of phosphorus with that of nitrogen, as phosphorus has large size as compared to nitrogen, so phosphorus both are in same group, but phosphorus due to large size has strong nucleophilic character as compared to that of nitrogen, which has small size, so less nucleophilicity. This nucleophile, you can see here, the lone pair of phosphorus attacks on the alpha carbon, which is directly attached to halogen. You know that due to high electronegativity of halogen, this carbon, that is alpha carbon, is partially positively charged, and so electrophilic center available for the attack of a nucleophile. This lone pair attacks from backside on this alkyl halide and moves to the phosphonium salt. The removed halo group remained with this phosphonium salt through the formation of a salt. Here is a question, why there is substitution and not elimination? And answer is also written as triphenylphosphine is a strong nucleophile and not a strong base. As we know, discussed I think also in some other lecture, that nucleophile means the less attraction of the nucleus on the valence shell lone pair, and lone pair are easily available to electron deficient position for attack. So we call this thing a nucleophilic reaction, and that atom having loosely bonded lone pair is called strong nucleophile. But in case of base, there should be small size which can easily attack on the hydrogen and easily remove it in the form of H plus ion. So as triphenylphosphine is a strong nucleophile, so it prefers to attack on the alpha carbon of the alkyl halide instead of beta hydrogen of the alkyl halide. If it attacks on the beta hydrogen, then there will be a chance for elimination, but as it is a good nucleophile, not a base, so it attacks only on the alpha carbon, and we get only a substituted product in the form of a salt and not an elimination product. This is the second step of this reaction mechanism. The phosphonium salt which was produced in first step is now converted or reacted with a base to be converted into a gellite, phosphorus gellite. This step is actually deprotonation of the phosphorium salt to form gellite. Strong base can be used to remove the proton from the alpha carbon of phosphonium salt. The alpha hydrogen of phosphonium salt is removed by the base. The resulting product has two forms, that is gelyne form containing double bond and the gellite form containing formal positive negative charges. Here are two questions. One is, why is it easy to remove proton from a CH bond? Normally a CH bond is not a polar bond, and it's tough to remove detach hydrogen from carbon in normal cases. But here it is easily removed from carbon. This thing can be explained due to presence of triphenylphosphine group, which withdraws the electron from this carbon and makes this bond slightly polar. Due to this triphenylphosphonium group, or you can see this positive charge shows that it is electron withdrawing group. So it makes this CH bond polar, and it becomes easy for a base to detach a proton or hydrogen from this alpha carbon and make a double bond there. Which form is dominating, gelyne form or gellite form? Normally, as we have discussed, there are two types of gelites. One is unstabilized gellite, other is stabilized gellite. In case of unstabilized gellite, the gelyne form, that is phosphorus gellite having C double bond P double bond, is dominating, and the reaction occurs mostly through this form. And in case of stabilized gellite, the gellite form is dominating. The charge separation is stabilized by the electron withdrawing group present in the phosphonium salt. So we get gellite form in dominating form, and the reaction occurs through this form. How the gellite form can be formed? Here you can see the reaction in which in case of unstabilized phosphorus gelites, triphenylphosphine is reacted with simply alkyl halide, where X can be iodine, bromine or chlorine. As we know, fluoro group is normally not used due to less reactivity, and iodo group is used most of the time due to less bond energy and more activity. It is heated to form phosphonium salt, and here you can see the phosphonium salt is written as a strong electron withdrawing group, and due to which its pKa value is 18 to 20. Here R can be alkyl group, or the hydrogen attached to alpha carbon is acidic in nature, and this acidity is shows by this pK value from 18 to 20. This phosphonium salt is further treated with base to form gellite, which is shown here. This base can be N-butyl lithium or LD. LD means lithium diisopropyl amide. It can also be used as a base. The features of these halide are alkyl groups are electron donating group, and so to stabilize the charge separation, as we discussed earlier, gelyne form predominates here and reaction occur through it. Phosphonium group is electron withdrawing group, so CH bond is acidic in nature here. Here is the preparation of another type of phosphorus halide, that is stabilized phosphorus halide. Here you can see triphenylphosphine is reacted with an alkyl halide also, but this alkyl halide contains a stabilizing group, like here is an ester group. This here also triphenylphosphine phosphorus attacks on the alpha carbon, that is carbon attached to bromine, and we get the halide. Phosphonium salt is it. Here can be a question that phosphorus attacks on the carbon attached to the bromine and not on the electrophilic carbon of the ester linkage. This can be answered as the lone pair of this oxygen of this alkoxy group moves towards the carbonyl through resonance, and this decreases the electrophilic character of this carbon, and the carbon directly attached to halogen has more electrophilic character, so the lone pair of phosphorus attacks on this carbon, and we get this product of phosphonium salt, and which in the presence of base removes the proton, and we get resonance stabilized product. Here you can see the negative charge on carbon is easily stabilized by this carbonyl of ester linkage, so this is named as stabilized phosphorus halide. The different features of this electron withdrawing group stabilizes the charge through resonance delocalization. Halide form in this case predominates and reaction occur through it, and also two electron withdrawing group are present there, so it will be more acidic. It will be more acidic. The CH bond in this case will be more acidic and can be easily removed by a weak base also. Here is written, you can see phosphonium is electron withdrawing group and the carbonyl is also electron withdrawing group. So two electron withdrawing group decreases its pK value will be too much low as compared to that of unstabilized phosphorus halides. Here is the last step of this mechanism, that is olefin formation. The halide produced in the last step reacts with aldehydes or ketones through a cyclic mechanism to form olefin. And here you can see the mechanism. The halide contains two charges, positive on phosphorus and negative on carbon. The carbon acts as a nucleophile and attacks on the carbon of electrophilic carbonyl and makes single bond between carbon and oxygen. Oxygen gets the negative charge. This negatively charged oxygen attacks on the phosphorus to form a four-membered ring, also known as oxaphosphetane. These two first steps, that is the attack of the nucleophile on electrophilic carbon and then attack of the oxygen on the phosphorus to form a cyclic, these two steps can occur simultaneously. Simultaneously mean at the same time, occurring at the same time. In the last step, this oxaphosphetane is broken into two products in a cycling manner. The two sigma electrons between carbon and phosphorus are moved towards carbon-carbon to form a double bond, and the two electrons between carbon and oxygen are moved towards phosphorus and oxygen to form a double bond. So we get triphenylphosphine oxide or triphenyl oxophosphine, and along with the alkene as product. Here we can ask a question, why this type of breakage is happening there. If you see the carbon oxygen bond and phosphorus oxygen bond, the phosphorus oxygen bond is more polar, more stronger as compared to carbon oxygen bond, so this bond can be broken easily as compared to phosphorus oxygen bond, so this has to be broken to form phosphorus oxygen double bond. If we compare this carbon phosphorus bond and carbon carbon bond. First, this bond between carbon oxygen was broken and phosphorus oxygen double bond was formed. In that case, so phosphorus will have to break this bond also, and so this these electrons move towards carbon-carbon bond, and we get an alkene. The basic initiating step is the breakage of carbon oxygen single bond as compared to other like phosphorus oxygen bond, and we get the final product of alkene and triphenylphosphine oxide, या triphenyl oxophosphorate. Here is the stereochemistry of this reaction. If we are moving with unstabilized phosphorus halides, then we have discussed earlier that it uses its Gilene form to reaction to react with the aldehyde or ketone and produces Z alkene predominantly. Here is the example in which you can see that there is a phosphonium halide, a phosphonium salt. Here is phosphonium salt which is reacted with a base to potassium hydride to produce phosphonium halide, which contains only alkyl group. So it is unstabilized phosphorus halide which reacts with aldehyde to form a Z alkene. In case of stabilized phosphorus halides, which reacts with through its halide form and produces E alkenes predominantly. Here is the example in which you can see a halide containing ketone as electron withdrawing group, which reacts with aldehyde in using water as a solvent and temperature of 20 to 90 and time 5 minutes to 2 hours. This varying temperature is because there is no specific molecules in this reaction. They are talking about the general reaction. Here is the aldehyde with general R group and the halide is with general R prime group. So therefore the conditions are not fixed. And we get the alkene with actually E alkene transform. Here is another reaction modification of this Wittig reaction by Socklosser, which is known as Socklosser modification. Socklosser modification was basically to get E alkene by using Wittig reaction, which normally gives Z alkene. The reaction proceeds mainly through erythrobutane intermediate which produces Z alkene. Erythro means identical groups are on the same side. But Socklosser modification converted erythrobutane into trio by the use of phenyl lithium at low temperature, so which in turn produced E alkene. Trio means identical groups are on opposite sides, so we will get the E alkene instead of Z alkene. Here is the reaction, overall reaction for the Socklosser modification. You can see here is the halide which reacts with this aldehyde, aliphatic aldehyde in tetrahydrofuranous minus 78 degrees C to produce erythrobutane. Erythro mean similar identical groups are on same side. If we warm it, we get Z alkene, that is similar groups are on same side and Z alkene. But if we treat this erythrobutane with phenyl lithium in tetrahydrofuran at minus 78 degrees C, this makes the stereo of this intermediate in such a way that we get threobutane. Trio mean the same groups are on opposite side, and in the end we get E alkene in which similar groups are on opposite side. This is called Socklosser modification, which was applied to Wittig reaction for the conversion of aldehyde or ketone into E alkene instead of Z alkene. As we discussed earlier that unstabilized phosphorus halides give Z alkene and stabilized phosphorus halide give E alkene. Now we will get through this point in some type of reaction mechanism. Here you can see that aldehyde or ketone reacts with phosphorus halide to give an early transition state. Early transition means that it resembles the reacting species. Also, this can be seen in another way like this. This thing is further converted into a cyclic molecule having 4-membered ring that is also called oxaphosphetane, and this molecule is irreversibly converted, that it is not converted back into its transition state or reactants. It only moves towards the product. And in this oxaphosphetane structure, you can see the same groups are on same side, and we get the product in which same groups are same side of the double bond, and so we get cis alkene or Z alkene in this case. Here is the second, the stabilized phosphorus halide, which gives E-alkene predominantly, and you can see the mechanism here. Aldehyde reacts with phosphorus halide and form a betaine, which reacts. And you can see here are two products. One is betaine, second is major thermodynamic product. In both of these cases, you can see the difference that R and ester group are on same side in betaine, and here major thermodynamic product is in which R and ester group are on opposite side. When they are on same side, they are slowly converted into oxaphosphetane, but when they are on opposite directions, that is trans to each other, they are converted into oxaphosphetane too much fast, and so we get this thing in major percentage, and this thing moves to the production of transalkene or E-alkene. So by using stabilized phosphorus halide, our major product is transalkene or E-alkene. Here are some advantages of using Wittig reaction for the preparation of alkene, and some limitations also. First, we talk about the advantages. Alkenes can be synthesized from aldehydes and ketones. Okay. And second, tolerance of carbonyl compounds with many different kinds of functional groups like OH, OR, etc. by the Wittig region. Wittig region mean phosphorus halide. When we use phosphorus halide, the carbonyl compounds do not interact with the species present in the phosphorus halide. They interact directly with the phosphorus halide through the alpha carbon acting as a nucleophile, and we get the product of alkene, and there are no too much side reactions. The geometry of the double bond can easily be predicted by halide nature, that as we have discussed, we are using stabilized halide, then we get E product, and if we are using unstabilized, then we get Z products, Z product, Z alkene. The limitations of Wittig reactions include both E and Z double isomers can be formed and in normal conditions. This thing makes tough for us to isolate the products from the reaction medium, and for the organic synthetic point of view, this thing is not too much good for an organic chemist. The reaction speed is very slow when sterically hindered ketones are used. The yield is also low for these reactions. Second is the case that if we use bulky ketones, that is ketones having bulky groups, then the rate of reaction becomes too slow, and we get the product, but too much time is required, and also yield is too much low in that cases. And in the last, aldehydes can easily undergo oxidation, decomposition, or even polymerizations. So this is if you say that it is the nature of, if it is the nature of aldehyde, then why we are discussing here in the case of Wittig reaction that nature of aldehyde is oxidation, decomposition, or even polymerization? Then what is the wrong with the Wittig reaction? Actually, they want to say that the conditions present in this Wittig reactions are favorable for the aldehydes to be oxidized, to be decomposed, or to be polymerized to some other products, and we have deviated product, we will not get the required product. Now, as we have discussed the Wittig reaction, which is used to convert aldehyde or ketones into alkene. Another reaction which is used for the same purpose is HWE, Horner Wordsworth Emmons reaction. The difference between these two is that Wittig reactions use aldehyde and ketone. HWE also uses aldehyde and ketone, but HWE makes the reaction of aldehyde and ketone with phosphonate stabilized carbanions. And Wittig reaction makes the reaction of aldehyde and ketone with phosphonium gilite. And if we compare the reactivity of both phosphonate stabilized carbanions and phosphonium gilite, then phosphonium gilite bears the neutral form also, in addition to gilide form that we call gilene form. And therefore this thing makes the reactivity of phosphonate less because it becomes more stable, so its reactivity becomes low as compared to phosphonate stabilized carbanions, which have charged species, and charges are more reactive as compared to neutral species, so they easily react towards the aldehyde or ketone. Second case is the HWE byproduct is dialkyl phosphate salt, which is easily removed by water in the last step. But in case of triphenylphosphine used in Wittig reaction, we get the byproduct of triphenylphosphine oxide, which has some problems during the workup process. And in the last, SWE produces E alkenes predominantly, and Wittig reaction produces Z alkene. But this thing should be clear that we can produce Z alkene from SWE by using some specific conditions, and also we can produce E alkene from Wittig reaction by using some specific conditions. Here are some synthetic examples for the Wittig reaction. In first example, you can see cyclohexanone is converted into methylene cyclohexane, which is converted into alcohol form. Second is conjugated cyclohexanone, which is converted into corresponding conjugated alkene. Similarly, in third reaction, you can see the electron with trying group is present color, which gives stabilized gilite, and we get transalkene, that is E alkene. In fourth, there is aldehyde, which has also reacted with alkyl bearing electron with trying group, and we get transalkene with respect to this one. Wittig reaction can be applied to cyclic compounds also, that is you can see here as a cyclic ketone, which on reaction with the gilide converted into cyclic alkene. And in second example, there is camphor, which is converted into also alkene, corresponding alkene with 91% yield. And you can see in the last example there is a aldehyde group present on aromatic ring containing some in the form of salt, and which on treatment with the similar conditions of this reaction, we get 62% yield of the product bearing alkene. So this reaction is also very useful for the preparation of alkenes, but on comparison of Wittig reaction and HWE reaction, preferably HWE reaction is performed, but it depends upon what type of product do you want, that is Z alkene or E alkene, so we will use the conditions which will favor our required product. This is about today's lecture on Wittig reaction, and thanks.